Hi everyone. This is the first video for Unit 7, which is chemical equilibrium, or just plainly equilibrium. And in this video, I want to describe dynamic equilibrium, and later we will make connections between this unit and the previous two units where we talked about reaction rate and spontaneity. Again, this is Unit 7, which is equilibrium. And we're going to start with a reaction to help us describe dynamic equilibrium. Call this intro, dynamic equilibrium. Let's use a reaction H2 gas plus I2 gas. We're going to use what's called an equilibrium arrow, which is a barb pointing to the right and a barb pointing to the left. Gives us 2 moles of HI gas. And we're going to illustrate this reaction using a graph. And on the y-axis, we'll have concentration of each of these components. And on the x-axis, we'll track the progression of the reaction and each component versus time. We'll make this kind of long. Let's suppose that at time 0, we have this amount of H2 in the reaction flask, and this amount of I2, and this much of HI. No HI, 0 concentration. Now, I know what some of you are thinking. You're thinking, well, this is not correct because it's a 1-to-1 ratio. Well, I am purposefully giving us an excess of H2. You may recall this as a type of limiting reactant problem where I2 will run out first, and I2 is a limiting reactant. I want to use this example, though, to demonstrate dynamic equilibrium because at the very end we will have more H2 than I2. So as the reaction progresses, you know that H2 will be depleted. It will be consumed. And let's say it consumes like this rate. At some point, it's going to hold steady. It's not going to go to 0. For most reactions, the reactants actually don't go to 0. For I2, it will also decrease. And it won't get to 0, but it will be less than H2. So what's happening with HI? HI is growing. And you know from your rate unit, it grows faster at the beginning and then levels off. But look what's happening when given enough time. Your concentration of HI, your concentration of H2, remember the brackets, the square brackets means concentration, and that concentration will be in most likely molarity. All these concentrations at some point hold steady. Let's say maybe around this point right here. At this time, you can say that your reaction has reached dynamic equilibrium, or simply it's reached equilibrium. But we'll use the word dynamic for now. Dynamic equilibrium. What that means is that these concentrations hold steady. What about the time before we reach this time? That is considered pre-equilibrium. So from 0 to that time, this is pre-equilibrium. Okay. Next, I want to try to connect this with the previous units. This is part B. What is the connection between dynamic equilibrium and terms that we've learned before, such as spontaneity and reaction rate? So connection to, let's say, free energy and kinetics. If you recall, the free energy unit was unit 6, the previous unit, and kinetics was unit 5, 2 units ago. Okay. Let's start with free energy. We know that for delta G, for a reaction to be spontaneous, all of this is review. If delta G is negative, the process is spontaneous. When we say the word spontaneous, we mean that it goes in the forward direction. So there are two things that go with this word spontaneous. It goes in the forward direction, the way the reaction is written. And actually, I should say that it's I should actually say it's favored in the forward direction. And also, eventually, you'll get more products than reactants. Eventually. Don't worry about the actual amount or the molarity. In general, you'll get more products than reactants. Not in this video, but in the next video, we'll talk about the ratio between the products and reactants. So that's when delta G is negative. But we could also connect this to kinetics because it was very brief, but I mentioned that when delta G equals 0, it's neither spontaneous nor spontaneous, right? It's what's called at equilibrium. That's our connection with this unit 7, talking about equilibrium. But what exactly does that mean? We mentioned that when it's at equilibrium, that the rate in the forward direction, FWD, equals the rate in the reverse direction. So the products and the reactants are still moving back and forth. It's just that the overall concentrations are not changing. That's what we mean by dynamic, that there is a forward direction, a forward rate, and a reverse rate, and that never ends. It's not 0. These rates are not 0. So this is where we get the term dynamic. Let me just make sure I'm not missing anything. Okay. So what I want us to look at is the illustration. So let's look at the illustration on the cover. It talks about population and the movement of people. This illustrates dynamic equilibrium. So initially, when we have a lot of people in country A, it's overcrowded. You could think of it as we have a lot of, excuse me, a lot of reactants. What happens is borders are open and it has time to equilibrate. People will move into country B where there's more space. Eventually, though, you're not going to have all of the people in country A move into country B because you'll have the same situation. You'll have overcrowding. So at some point, you'll have a steady amount of people in country A and country B, but the borders are still open and there is free movement between country A and country B. So even though the total number of people are steady in country A and country B, by the way, I'm not saying that they're equal, I'm just saying that they're steady, then you still have people moving back and forth, but it's just at the same rate. If 4 families move into country A, then 4 families will move from country A to country B and maintain the population of both country A and country B at equilibrium. So those populations at some point will be maintained and they'll be steady. So it will reach dynamic equilibrium. The last thing I want to mention, okay, I think we're done with connecting to free energy, delta G, and kinetics. Let me just double check that I gave everything that I want to give. I think we're good. The last thing is I just want to briefly talk about this idea that a reaction can still have reactants present and products and establish equilibrium. That's in contrast to what I call a reaction going to completion. So the last topic in this video will be completion versus equilibrium. Depending on who you talk to, there's actually no reaction in the universe that goes to 100% completion. There'll always be some reactant. It could be a very, very tiny amount, but there's always some reactant. But I'm going to think about completion theoretically, where you make 100% of the products that you can make. So for instance, combustion. Combustion gets very, very close to completion because it can't reverse. So for instance, if I have sucrose, C12H22O11 plus O2, leave a space. I'll use a regular arrow, CO2, leave a space, you're going to balance this, plus H2O. Can you balance this reaction? We have 12, 12, and 11. Because CO2 is a gas, it escapes. And when it escapes, you don't have CO2 to go in the reverse direction. Unlike here, the HI can decompose into H2 and I2. So it escapes and reaction cannot reverse. Okay. So what I would say is that this reaction goes to completion. Most reactions do not go to completion. Most reactions establish an equilibrium. Okay, in the next video, I'm going to discuss what to do with these concentrations to get what's called an equilibrium constant. So again, let me just write this example. This is an example where you reach equilibrium. H2 gas plus I2 gas, equilibrium arrow, 2HI gas. And in the next video and the following videos, we're going to ask ourselves, what are the concentrations of H2, I2, and HI at equilibrium?